Okay. So, just let us try to recall what we did last time. We discussed linear systems. For linear systems, we meant the principle of superposition should be valid. That is, this is a system which takes x n as a sequence as an input, produces y n, system is represented by an operator t, just an operator which works on x n in some way or other and gives you y n. This system will be called linear if the principle of superposition holds good. What is superposition? That is, if I give one input say x 1 n, find the output say y 1 n, which is t working on x 1 n. Similarly, if I give another input x 2 n and suppose the output is y 2 n, which is t working on x 2 n. Then, if I do not give x 1 or x 2, but if I give a linear combination of them, that is x 1 n multiplied by c 1, that is all samples multiplied by a constant scalar c 1, x 2 n multiplied by c 2, all samples multiplied, c 1 and c 2 could be 1 also. So, this is more general combination, and then I add the 2. So, I get a new sequence. If I input that at the input of the system, the output should be, if it is linear, output should be this, that is this component and this component, their addition. What is this component? That is the response of the systems due to this part is here, where c 1 constant it comes out, that is c 1 times a sequence. If I give as input, the output will be same as if I give x 1 as input and then at the output I multiply by c 1, that is at the output this much multiplied by c 1, the constant can come out. So, it is one response due to this part, this is another response due to this part, and for the combined sequence the output response is a combination of the two, addition of the two. That is system output, in philosophically speaking, system output due to multiple inputs is a summation of the individual responses due to those respective inputs, separate inputs. This is a mathematical expression that if I give a linear combination of two sequences x 1 and x 2 n, system output will be what? Same c 1 times response due to x 1 and same c 2 times response due to x 2, their addition. Okay. And another thing was very important, that was shift invariant, which is related to time invariance if the sequence is obtained from a time signal. That is, suppose this is again a system, it takes x n as input, y n as output, and for convenience in understanding the x n sequence which is shown here, you imagine that it was obtained by sampling an analog function. So, this is actually correspond to a sampling period 0, this is t, this is 2 t, this is 3 t, this is 4 t, though I do not write t. When it is sequence, I told you we only mention the index number. So, we do not care about the time, but in your mind we know this is for 0, this is for t, this is for 2 t, this is for 3 t, like that, one sequence. Such a sequence is given here and some output we are getting. Okay. Now, question is, if this sequence is delayed in time domain, there is a shifted. Shifted means if I shift it by say m number of points. So, 0 goes to m, 1 goes to 1 plus m, that is m plus 1, 2 goes to m plus 2. Okay, so, the same sequence you see I have just shifted. Physically it means in time domain I am introducing a delay. 1 delay means t, 2 delay means 2 t, 3 delay means 3 t. So, m times, since 0 goes to m times t, 1 t, 2 t, so m t. Similarly, this point which is capital T, that goes to m plus 1 into t, capital T. So, we add another m into t delay, so m plus 1 t. This is 2 t, add another m into t delay, m into t, you go to here. That means, in terms of time, this sequence is delayed. It as a sequence, I say it is just shifted, because I do not write the time here, I just count the indices. So, 0 goes to mth point, first goes to m plus 1s, second goes to m plus 2, like that. So, it is shifted, but actually in real time it is delayed by m into sampling period t, that many sample period, that many sampling periods, the entire thing is delayed. If I give that to the input system and the system behavior, suppose it is not changing, it is permanent, it is constant, it does not change. So, if I give the current input, I get a current output. If instead of giving the input now, if I delay it by some amount of time and then give the same thing, then output also in nature will be same as the current output. Only thing is it will be placed from m onward. Okay. That means, if input is shifted by some amount, output, current output also will be shifted by the same amount, and that should not depend on the choice of m, it should be true for any choice of m, positive, negative, very high, very low, all. If that be, that the system property is not changing over time, then it is called shift invariant or time invariant. When I directly show the time points 0, t, 2 t, 3 t, etc., time invariant, but when I just write the index numbers and carry out my business like that, then I call it shift invariant. Okay. Mathematically it means, suppose I give x n, output is x n as input, output is y n, which is t x n, and now I shift this sequence by m, x n minus m, which is a shifted version. So, I call it say g n, that is this sequence I call g n, okay, because it is shifted version of original x n, shifted by m, everybody got shifted by m, I call it g n. If this g n I input to the system, the new output which I call y 1 n, that is response of the system due to g n, that should be nothing but shifted version of original y and shift by the same amount m, all right, and this should be true for any m, then it is called shift invariant. So, now we will be considering systems which are both linear and shift invariant. Sometimes we call linear and time invariant, because I mean we use this term time invariant so often in analog domain. So, by bad habit you can say we carry it over here also, but strictly it is shift invariant. Okay. So, now consider a system. This is x n, this is y n. Now, remember yesterday in the last class I showed that any sequence x n can be represented as superimposition of deltas, delta sequences. Let me see if I can find out the slide. Yes, here. Suppose this is a sequence x 0, x 1, x 2, x minus 1 like that, but this is same as start with one subsequence with height with one sample here x 0 and all are zeros. Then another subsequence. So, this is nothing but x 0 into delta n, because delta n has 1 here and 0 everywhere. So, if you multiply it by x 0, 1 becomes x 0, zeros remain 0. Then another one, I pick up the x 1 from here, put it here, all other points are 0. Then this will be nothing but x 1 into delta n minus 1, because delta n minus 1 means the 1 from here will be shifted here, because it is delayed by 1. So, it will come here, that 1 value multiplied by x 1. So, total height will be x 1, others are zeros. Then I pick up x 2, bring it here, all other points are 0. This will be nothing but x 2 delta n minus 2, that is delta n means 1 here, that will be shifted by 2. So, it will come here, then multiplied by x 2. So, overall height will be x 2, zeros everywhere. I consider x minus 1 from here, put it back in its place, all other points are 0. This will be nothing but x minus 1 delta n plus 1, delta n plus 1 means n minus minus 1, that is n plus 1, that means it will be shifted by minus 1, that is it will go delta n had a 1 here, that will be instead of going to the right, it will go to the left, come here, then multiplied by x minus 1, so overall height x minus 1, so on and so forth. And you see, if I add all of them, you get x 0 plus zeros, so x 0, x 1 and 0 0 0 elsewhere, so x 1, 0 0 x 2 0 0 0, so x 2. So, you get back your original sequence. That means, original sequence x n is a superimposition of various subsequences. One is x 0 into delta n, this one is x minus 1 delta n plus 1, that is this one is x 1 delta n minus 1, that is this one, x 2 delta n minus 2, that is this one, this. So, we can write in a compact manner in this way, x r delta n minus r, that is x 0 delta n minus 0, x 1 delta n minus 1, x 2 delta, like that. So, that is what I will be using now, this here, you see, the same thing I am writing here. So, y n is t working on x n, right. Now, x n I substitute by this. Now, the system is linear. and it is a summation. It is a summation of various subsequences, right. So, overall response will be summation of individual responses because of linearity. Overall response, that is for your sake, if I write the summation in the detailed way, in the in this manner, x minus 1 delta n plus 1, x 0 delta n, x 1 delta n minus 1, x 2 delta n minus 2, dot 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 dot. This is summation. So, this t working on this total, if t is linear, it will be same as this t working on the individual ones and their summation. And when t works on the individual one, this is like the constant. So, it will go out, this is the sequence part. So, it will be like dot 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 x minus 1 will go out, t will work on that. Then x 0 will go out, t will work on that. X 1 is a constant again, so it will go out t, because this is the sequence, it has n. This does not have n, anything is a function of n is the sequence. So, t will work on the sequence, this is just a constant, and dot 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 dot. In general, so that means in this expression you can write t will work on this total, and then this constant will go out, t will work on this. So, x r t working on delta n minus r. This is nothing but this summation, I am writing in this way. All right. So far so good. Now, suppose if you give delta n here and the corresponding output y corresponding output say t delta n, you record, okay, and call it h n, call it unit sample response, and by loose thing we sometimes call it impulse response, but actually it is unit sample response, okay, because this is very much by this symbol looks like the impulse function of analog. So, we call it by mistake, but the mistake is accepted as impulse response. Actually, it is unit sample response. So, if I say impulse response, you try to understand that I am meaning unit sample response. So, suppose delta n has this, that is unit sample response of this system, that is you give in delta n as input, what is the output you record, you call it h n, which is unit sample response. Okay. So, t delta n h n, but if the system is shift invariant, then if delta n is shifted by r, it was delta n, now n minus r. If it is shifted by r, output new output t of this actually will be nothing but original output shifted by the same amount. So, this will be nothing but h n minus r. T delta n was h n, if delta n minus r, that is if the sequence is shifted by r amount, new output will be shifted of version of the original one h n, and amount of shift will be same r, because it is shift invariant. So, then we get this result. Okay. This is a famous thing, it is called convolution between x and h. Okay. That is, we symbolically we represent this by like this. Let me explain the meaning of this symbol. Whenever you come across this x n star h n, first guy is x n, second guy is h n. Then what you have to do? You first bring a summation, okay, then bring an index r or L or M or anything but n, not n, because by this convolution you are trying to find out y n. So, n is your choice, you wanted to find y at a particular n of your choice, n is fixed by you, that n in this summation is fixed, r is only variable. So, remember n is fixed by you from here, from left hand side, you want to find out the output at a particular n of your choice, that n went in here. Okay, r is variable. So, that is what I am saying, when I am writing in this form, you do not bring n here, bring some local variable r or L or M or K or I or anything. and you should have the range from minus infinity to infinity. I am telling you, if you get this expression, what is the meaning? First you bring a summation symbol, bring a local index or L, M, N, anything, but not N. Take it from minus infinity to infinity to be most general. Then first term will be first guy, second term will be second guy. For the first term, you make it a function of R, this index. For the second term, you make it a function of minus of R and then plus N. N is your choice, you want to carry out this at a particular N, so that N minus R. So, first bring a summation, then a local index R from minus infinity to infinity, write first guy X, second guy H, within bracket for the first guy R will come, within bracket for the second guy N minus R will come. This is the convolution. All right. This convolution has some properties. First, this is called commutative. Commutative means x n convolved with h n will be same as h n convolved with x n. Commutative, like I mean, if you take two decimal number, their addition is commutative. A plus b is same as b plus a, but subtraction is not commutative. A minus b is not same as b minus a. Similarly, their product is commutative. A into b, b into a. Okay, they are commutative. But division is not commutative. A by b is not same as b by a. Okay. By the way, product of scalar is commutative, decimal scalar. A into b same as b into a. But if you give matrices, one matrix A, one matrix B, then A into B is not necessarily same as B into A. Okay. So, remember these products, as long as they are scalar decimal numbers, their product is commutative. But if instead of scalar you have matrices, then there is a problem. Anyway, there are plenty of commutative operations in real life. Convolution is one of them. How? This I have to show. Now, in this summation you see, I play a game. N minus R, I give it a name small m. There is n minus R, I call it m, which means R, because n is fixed, R is a variable, I am substituting, I am bringing m to replace it. So, what is R? R is n minus m. So, in this summation, x of R instead of R, I should have n minus m, and h instead of n minus R, I should have m, and I can write h first, x second, because this is just two scalar numbers multiplied. So, this into this is same as this into this. So, I can write h m first, x n minus m, summation. Earlier it was about R, now it will be over m. Now, you see when R goes to minus infinity, it is n minus minus infinity, so n plus infinity. So, m goes to plus infinity, m should be plus infinity. Okay. And when R goes to minus infinity, sorry, when R goes to plus infinity, n minus plus infinity, that is minus infinity, m goes to minus infinity. That means, it should be from plus infinity to minus infinity, in the opposite direction, from plus infinity we will go back to minus infinity. But it is a discrete summation. So, discrete summation, if you sum from right to left like this, like this, like this, or left to right like this, like this, like this, you cover all the points. So, it does not make any change. Therefore, summation from plus infinity to minus infinity or minus infinity to plus infinity, you cover all the discrete points on this time axis, right. So, it does not change. So, I again write as m minus infinity to infinity. Now, look at this thing. There is a summation, there is a local index m, range from minus infinity to infinity, like here, summation, local index r, minus infinity to infinity. First guy is h, second guy is x. In h, within bracket this local index come. In the case of x, what comes? N minus the local index. So, it is like convolution between h and x, evaluated at nth point. So, this is the n, like here also n. This shows that x n star h n is same as h n star x n. We started with x n star h n. I made this substitution, and this immediately becomes h n star x n. First guy is h, function of m, second guy is x, function of n minus m. Here it was function of r, second guy was n minus r, because r was replacing m. all right. And now I tell you, always whenever you solve problem and all that, instead of choosing the convolution this expression, for convolution this expression, you always choose this expression, this is the equivalent expression, this is the rule of thumb, then your problem becomes lot simpler. You will see, I mean steps will become simpler, the whole problem becomes simpler. If you stick to this original form, things become little complicated. That is why instead of this form, we always choose this form. This is a rule of thumb, it comes out of practice, out of experience, this is what I observed. So, I am telling you, this as a tip I am giving you, that whenever you have convolution between two sequences x and h, like xn is the input, hs is the impulse response of a system, instead of taking it as xn convolve with hn, that is this formula, you reverse it, write it as xn star hn, okay, this formula, and then your subsequent steps become easy. This is a rule of thumb. So, what we have proved here is that convolution is commutative. Okay. The next thing is convolution is distributive. Suppose I have got x n, I have got a system h 1 n. So, it produces an output y 1 n, that goes into another system. This is linear and shift invariant. So, it is characterized by its unit sample response, output is given by the convolution between the two. This is a linear shift invariant system. What we have seen a little while ago, that for a linear and shift invariant system, the system is fully given by characterized by its unit sample response, that is if you give delta n as input, the output whatever it is that you write. In that case, for any other input x n, you can carry out the output calculation, that is nothing but the convolution between them. So, y 1 is a convolution between x n and h n, and equivalently between h 1 n and x n, because the convolution is commutative. Then this y 1 n goes to h 2 n. Again, so this is the input now for h 2 n, and new output is y n. So, y n is convolution between y 1 n and h 2 n, or between h 2 n and y 1 n. What is h 2 n? It is another linear shift invariant system. Since linear and shift invariant, it is fully characterized by its unit sample response, that is if I give delta n as input here, the output will be h 2 n, that I record and put back here. In that case, for any other input, say y 1 n, corresponding output will be a convolution between them, between y 1 and h 2, and equivalently between h 2 and y 1. What I will show is that you can interchange the two and still you will get y n. That is, I can first bring h 2 n, this input is x n. So, this output will be different now, call it y 2 n, and then you have first one h 1 n here, I am interchanging, and still you will have y n. This is my claim y n. That is, if you call it y prime n, we will show that y prime n is same as y n. So, the two can be interchanged. Okay. How to show that? So, let us work out y n. Y n is a convolution between these two, but I told you always choose convolution instead of not between y 1 and h 2, but between h 2 and y 1. So, you write summation and index r h 2 first or y 1 n minus r. What is y 1? There is a convolution between them. Convolution between x and h 2, x and h 1, or equivalently h 1 and x. I will prefer h 1 and x. So, I introduce an index m minus infinity to infinity, bring m here and x, not n, because I want to find out y 1 at n minus r. So, n minus r minus m. Instead of n, I have this much index coming from here. Earlier, I had y 1 n and now I have x, that time I had x n, now y n minus r, so it is x n minus r, then minus m. All right. Now, what is this summation? This is an outer summation. Outer summation means every time r you take a value, say maybe I h to r, one value, 0, 1, 2, minus 1, minus 2, like that. Keep that r, for that you carry out this full summation, okay, for various values of m. Multiply that by h to r. Then take another value of r, hold that value, and again carry out this summation. Put that, you have to put that r always, whatever r you are choosing here, you have to bring it here. All right. Then this thing is same as, so this is the basically h to r, for that you are carrying out a summation. Then h to another r, you are carrying out a summation, you are putting that those r's here. Okay. You will have the same thing you can write like this. You bring in h to r from outside, that is first you are working out a summation, then multiplying by h to r. It will be same thing if h to r is brought inside summation, it multiplies every term here for each m. Like if you expand this summation, every term you multiply by h to r. So, h to r every term, h 1 m, every term means for each m. All right. That is, what is happening is this summation you are expanding. One term, another for various m. Every term you are multiplying by h to r, same h to r, same h to r for various m. That is, a typical term is this, it is multiplied by h to r, and then you are doing for all m. You will have the same thing, that is, instead of first carrying out a summation, then multiplying by h to r, you bring h to r inside, multiply everybody by h to r and then add, you will have the same thing, right. But now what will I do? I will take h 1 m. What I can do? I can interchange the two summation. Why? Because how is the two thing going? First you are choosing an r, then you are carrying out a summation for all m. Then another r, again you are carrying out a summation for all m. Okay. You will have the same thing if I fix m and then carry out this summation for all r. Again another m, carry out the summation for all r. Okay. So, this entire thing is a function of r and m. Okay. So, this summation means what? R equal to, suppose you are choosing 1 and then you are carrying out all summations. If r equal to 1 and say m, you are say m equal to 1, 2, 3 dot 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 dot. Okay. Then again r equal to 2. So, r equal to 1, 1, 1, 2, 1, 3 like that. Okay. Then again r 2, 2, 1, 2, 2, 2, 3 like that. Instead, you can hold m equal to 1 first, take r value r, vary r, take r over the entire range, then take next value of m, vary r over the entire range, take next value of m, vary r over the entire range. You will cover the same points only. Okay. So, either you first fix r, for that r inside carry out this evaluation for all m's and add. Take another r, again for that r inside you carry out this summation, okay, for all m and add. Alternatively, you can fix m and vary r over the entire range, then take another m, again vary r over the entire range, take another m, vary r over the entire range. You will cover all the points, all r m pairs or from here in m pairs will be covered. R will be from minus infinity to infinity, m minus infinity to infinity. That is, either r you fix and then vary m, another r again vary m over the same range, another r again vary m over the all range, same range. or alternatively every time you fix m, then vary r over the entire range. Another m, again vary r over the entire range. You will cover all possible pairs of R m either way, which means I can interchange the two summation now. I can bring the inner summation over m outside, I can bring summation over R inside, and this entire thing. Now, from this H1 m can be brought out because that does not depend on R, it is like a common for every term, every other terms dependent on R. The summation is over R, this depends on R, this depends on R, they will be inside. But this guy was here, but it is common, it does not depend on R, it is there for everybody in this summation. So, it can be pushed outside as a common, you carry out the summation first, then multiplied by H1 m. Okay. And x n minus r minus m, so I rewrite again x, instead of n minus r minus m, I can write as n minus m minus r, same thing. But what is this? This is convolution between H2 and x at n minus m. R is the local index, is r here minus r here. So, n minus m is fixed from outside every time, so inside the summation m is fixed, n is already fixed. So, this is a fixed number, r is only varying. So, the convolution between H2 and x. Okay. What was convolution between H2 and x? Y2. So, this means this is Y2, this is Y2, but at this point. That means this is H1m Y2, but at this point. Again it is a convolution between H1 and Y2, local index m come here with a minus sign here, n here. Okay, so, this is the convolution between n star Y2 n. So, that is what we have here then, you see. What we are getting? H1 convolved with Y2 or same as Y2 convolved with H1. And what is Y2? Y2 is we have already seen convolution between the two. Okay. So, Y prime n, this is same as Y n. All right. We started with Y n, and this is what this figure shows to be Y prime n. All right. So, this proves the equivalence, which means you can interchange the two. That is all for this session. Now, we will move to the next session.